Hi everyone. In this lecture, we're going to be covering section 2.3 in Daniel Steck's textbook. Oops. I think. This is actually a pretty long section. I think the next lecture is going to be on this section also, but that's okay. So we're going to talk about AC signals and complex notation. And actually, this section also leads into low pass filter, which is interesting. That is not a separate section, but it's okay. We'll deal with how we can separate this information out a little bit. Okay, so this section is going to teach us how we can represent sine and cosine function as complex exponentials. But first of all, like, why are we so interested in sine and cosine function? I mean, are we just all into triangles and stuff like that? But so what's actually important about sine and cosine function is actually that's how information actually gets sent back and forth. For example, my computer to the Wi-Fi router that's uploading this video, the information is actually sent by sine and cosine function with different frequencies, and then the amplitude of each of those frequencies actually tells you like what the digital bits that I'm sending up to the Wi-Fi router here. Same thing with your cell phone. Same thing with if you were listening to the radio, um, radio as in like the car radios, where the amplitude um, of each of the frequency tells you, you know, how to how the the singer or the music is actually being played, and therefore it represents the information that you're sending to, between the two devices. Okay, and so that's the reason why sines and cosines are useful. And so you can actually represent any periodic function as linear combinations, or also known as superpositions of sines and cosine function. And this is known as a Fourier transform. So for example, even a step function like this, that is kind of hard to see out here, but there's a step function behind here that's basically a box shape, right? The way this works is that, well, if I do a Fourier transform where you take 10 terms, meaning the Fourier transform is actually f as a function of t, and this a naught kind of sets, where the 0 is, so in this case, actually 0. But then you sum up multiple terms of sines and cosine functions. So you can see that for n equals to 10, it's looking like sine cosine-ish, right? It kind of looks like a wave. But then as you increase the number of terms that you're adding up, it becomes more and more closer to the square function that we're trying to represent. So these sines and cosine function of different ends. So these ends, where the placement is actually interesting, right? This n here, right? Because typically you have cosine of omega t, let's say, or another word, cosine of 2 pi times ft, right? These ends, right, are actually the frequencies of the sines and cosine function. Okay, in this case, the book chose to represent it as 1 over the period, but 1 over the period is the same as the frequency. Okay, and what happened is that these A's and B's, right, these are actually going to be the amplitude for each of the frequency of the wave you're adding into it. And that way, if you want to calculate, if you want to represent any periodic function, all you have to do is calculate what these A's are: A0, A1, A2, A3, and then all the B's for the sine function. And these can be calculated using this equation here, where you're just integrating from negative half the period to positive half the period for any end. And then you can actually calculate these A's and B's. And this is actually the information that we're sending back and forth between the Wi-Fi router, my cell phone, your digital TV, and all that stuff. Okay. So any information between two locations can be sent. If we want to figure out, send, these A's and B's, all we have to do is send this arbitrary wave. And then when you do a Fourier transform of this, then you get the A's and the B's out. The N's and the Bn. Okay. And then you have some numbers that, I want, this number to be 1, this number to be 2. Well, there's actually multiple of them. Okay. And this is how information actually gets sent between devices wirelessly. Okay. To make things simple, what we're going to do is we're going to deal with one frequency, but this frequency is going to be arbitrary. So this omega, right? Omega is 2 times the frequency, 2 pi times the frequency, right? So if we want a different frequency, we just have to change this to omega. So this is actually, can be different for different applications, for different wavelengths that different frequency of data you're sending. Okay, but we're gonna think of this as constant for now, and therefore we don't have to deal with it. And then if we can solve this problem for this one frequency, we can solve it for all the different frequencies because this omega is just a parameter. Okay, so in this case, right, the voltage that we're sending is going to be a function of time, right? In fact, right, so let's draw this up right now, right? Right, it has some amplitude V0, so it oscillates between positive and negative. Since its cosine starts at 1, so this is V as a function of time. Okay, and this V0 is arbitrary, as we said, and usually that's the amplitude, and that's actually a lot of times the information that we're sending back and forth between different devices. Okay, so just an example, so if we want to figure out if we're sending this AC signal, this is equivalent to an alternating current because it's a time varying voltage, right? We're sending the signal through a capacitor, right? Remember the capacitor, right? You can calculate the current through a capacitor by just differentiating the voltage with respect to time and then multiplying by the capacitance. Okay, if we differentiate this function, okay, the differential of cosine is negative sign, but what happened is that you actually pop out an extra factor of omega because that's considered a constant right now. What happens is that then you end up with negative omega c times V0, that stays there, times sine instead of cosine. Okay, but a sine function is actually, well, in fact, the negative of the sine function, this whole thing here, right, is the same thing as a cosine function with a plus pi over 2 phase shift. Okay, what do I mean by this phase shift? So let's look at this picture down here. So here, right, I plotted in blue. The function is just sine of x. Wait, down here, right, this blue function. Okay, cosine, right, is plotted as red. So hopefully that makes sense that they are, cosine starts at 1, sine starts at 0. Okay. If I plot y equals to negative cosine, which is exactly, I guess I plotted the opposite. But if I plot negative cosine of x plus a, where I'm going to make a pretty close to pi over 2, because what happens is that if I make this exactly pi over 2, the two plots will exactly overlap each other, and you actually don't see both of them. So that's why I shifted it a little bit, just to make it so that it's slightly different from each other. Okay, so if we have this phase shift of pi over 2, almost pi over 2, right, what happened is that it basically switches this cosine function into a sine function, so you can see that they are actually comparable to each other. Okay, so that's one way to think about that. Another way is just memorize trig identities so that you know all these trigonometry. Okay, all right, so that's how we represent the AC signal in our circuit, okay, with these sines and cosine function. Now we're going to complicate things just a little bit more, because what we're going to do is we're going to put this in the complex notation instead. Okay, so just to, I don't know if folks see this in their algebra class or trigonometry class, is that you can represent a number, right, in the real plane, but also in the complex plane. When you have a complex number, so usually it's represented with the letter Z. Okay, so some number plus I times B, where this is the real part, this is the imaginary part, and then the two of them together makes a complex number because it's more complicated. Okay. So, and then I'll explain why we're doing this in an electronics class. But one thing just so you can refamiliarize yourself with, what happens when you have numbers in the complex plane, is that, for example, here, right, you have the complex number 2. Let's go here, 2 plus 1i. Okay, so it goes 2 in the real direction, and then 1 in the imaginary direction. Okay, it's actually better if I write it here, so not in the way here. Okay, all right, notice that, right, there's some magnitude to this, and then there's also some angle to this. Okay, the cool thing is that if let's say we stay in the unit circle, okay, I'm going to break this down in 2 pieces. Okay, we can actually write this dependence on theta as a combination of cosine for the real part and I times sine for the imaginary part, right? Just like here you have this I in front of it. The I gives you the sine of theta gives you the vertical line here. The cosine of theta gives you the horizontal distance here, right? It's just like in your trigonometry class. Okay, and this allows us to basically represent any sines and cosine functions, okay, as a complex exponential. Okay, and this actually follows from Euler's formula, where e to the ix is actually easier to see it like this, equals to cosine of x plus I times sine of x. Okay, where this is the imaginary part and this is the real part of this complex number. Okay, so this is the complex number, this is the real part, this is the imaginary part. Okay. Okay, what we're going to do, right, remember that the voltage that we started with that depends on time, V naught cosine of omega t. Right, is there a negative sign? Nope. Okay, what we're going to do, oops, scroll too far. What we're going to do is we're going to complexify this. Okay, since this cosine x, right, so basically x becomes omega t, right, what we're going to do is using Euler's formula, so we're going to insert this cosine omega t into here, right? So since x is omega t, the sine also has to be omega t. We're going to have some amplitude in front of this. We call it V naught. Okay, so what happened is that the complex version of V, and it's represented by the book with this V tilde in here, and I'm going to warn you that the book will use this symbol for multiple purposes. In this case, it's just the complex voltage. It's going to be V naught e to the minus I omega t. So this is the same thing as writing V naught, big parentheses, cosine of omega t plus I of sine omega t, not 0. Okay. All right. Oh, already did it down here. Okay. So physically what happened is that since the function that we were originally representing is actually only the real part, so whenever we want to find the voltage as a function of t, we only take the real part. This RE stands for the real part of this complex voltage function, and the real part of e to the I omega t is actually just cosine omega t. and then this V naught just kind of follows along. So any number, right? Sorry, any voltage that depends on time can now be that's represented by cosine and a phase, and this phase allow you to shift things between sines and cosine, just as talked about before, right? And so both, all this stuff depends on time. The book doesn't write it all the time, but so any voltage can be represented by this V naught, which is the amplitude, times this e to the minus I omega t, and there's also a possibility of a phase shift. And it's actually usually better written like this. I don't know why the book writes it like this, where you factor out the negative I omega t plus phi. Oh, did it down here. Okay. And when we take the real part of it, right, this argument inside here becomes the cosine. You take the amplitude, and then you just ignore the rest of it. Okay. So why are we doing this? Okay. This allows us to do some interesting calculus because, right, one of the cool thing about exponential is that if I have, e to anything, okay, so to anything, right? Let's not do that. Okay. Anything times t, if I take the derivative of it, is basically this any, whatever this is, times the same thing over again, right? It doesn't change the exponential part. It just factor out this thing in front of it. Okay. So if we want to differentiate sines and cosines, so we have to remember, oh, is there a negative sign? Is there a positive sign? What's the sign flip? What is extra omegas coming out? If we differentiate this, right, which is this complex voltage function, right, the only thing that depends on time is this I, negative I omega t. So what happens is that this negative I omega t falls out of the exponential, and then you recover the same function over again. So you don't change from sines and cosine when you differentiate, which is nice. Okay. So if we compare both sides of this equation, what happens is that we can see that, well, the time derivative for the voltage function, right, is actually the same thing as just multiplying it by negative I omega. Okay, so this is the derivative of a monochromatic signal. Monochromatic means it's just a single omega or f, right, a single frequency. Okay. As I mentioned before, if you can solve it for one frequency, you can solve it for all the different frequencies, right? Because you just add out the different frequencies together. So if we take this to our capacitor equation, right, where the current is equal to the capacitance times the time-changing voltage, right, happen is that this is basically equal to, well, the I stays the same, right? The differential, right, of the voltage, I'm going to write this separately for now. We can replace this part by just negative I omega, C negative I omega, and then get the voltage back. I'm going to rearrange things a little bit just to make it look nice, right? You can see that this is the same thing here. We're doing this complex version of it. Okay. So we can see that I equals to some factor, right, that in the case where we're dealing with just one frequency as a constant, because omega is a constant, capacitance is constant, I'm going to write it like this, so it may even look more familiar. I, the complex current, 1 I omega c, the negative sign, right? And what happened is that this starts to look like almost, I'm going to actually call that the capacitive reactance, which is what we're going to talk about next. Okay. The book does this in the opposite order, but I really want to kind of clarify things so that people are not trying to memorize two of the same thing that are two things that are actually the same thing. So you just kind of, try to learn one thing that's, oh, okay, sorry. This will make more sense once I kind of describe it, okay? So this idea of reactance, okay, is going to come into play where it's basically going to be equivalent to kind of like a resistance to a capacitor, okay? And what's going to happen is that this is going to generalize to this concept called impedance. I think we already talked about this in the first chapter where I'm talking about it, but not really defining it very in the circuits yet. But I want you guys to start equating resistance with impedance, okay? And now I'm going to tell you to do the same thing with these concepts called capacitive reactance and inductive reactance. Just equate them to impedance, okay? And in real life, what happened is that everybody just uses impedance. Resistance is still used because resistance is actually, a special term. So all three of these terms means the same thing, because what happened is that you plug these things into Ohm's law, and well, this is called a generalized version of Ohm's law, where the voltage drop across some device, it can be whatever, it's going to be whatever this reactance is times the current, okay? And that's going to be interesting. This is supposed to be a question mark there, not a 3. Looks like a 3 to me, okay? So this question mark could be a resistor, and in that case, the X will just be a resistance. This could be a capacitor, right? In this case, it's going to be XC. This is going to be an inductor. This will be an XL, okay? And it's going to be very nice. And it's actually really cool that one thing that I always love about physics is that it combines multiple seemingly different concepts together, and it actually puts it all under one umbrella, and everything gets simplified quite a bit, and so you don't have to memorize as many equations. Okay, so what we're going to do is we're going to rearrange this equation here. I think we already did it. Okay, I'm going to do it one more step. That's just to familiarize ourselves with the imaginary number. Okay, so this I here is equivalent to square root of -1. Okay, so what happens is that if I multiply this equation by I on top, I on the bottom, that's still equal to 1, right? I can always multiply by the same thing on top and do the same thing on the denominator, and don't change the value of the function. Okay, so this is going to be equal to I tilde. Okay, on top we have negative I, right? On the bottom we have I times I, right? So I squared, and then we still have omega c on the bottom. I'm going to keep equating things. So if I square both sides of this, I basically remove this negative square root, right? So I squared, oops, there's only one side. I squared is basically equal to -1. Okay, so I tilde here, negative I on top. I squared is actually equivalent to -1 omega c. There's a -1 on top. These two actually cancel out. So what happened is that I omega c becomes like this. Okay, I'm going to rewrite this version of it so that we can compare. -1 I omega c. Okay, notice that when you move the I from the denominator to the numerator, it just picks up a -1. Same thing happens if you move an I from numerator to the denominator. It just picks up a -1. Okay. Okay. So that's basically what happened here when the book says we rearrange equation 2.34. We just moved the I from the denominator to the numerator. Okay. And this is what is known as the capacitive reactance. Okay. So the cool thing about this is that, well, the voltage across this capacitor is proportional to the current times something. Okay. And this is reminiscent of Ohm's law, where if you have a resistor, the voltage across that resistor is proportional to the current times R, but in this case, not R, but this complicated function equals to I divided by omega c. Okay. So this is commonly known as Ohm's law, or I like to call it the super Ohm's law, where you just expand Ohm's law to anything as opposed to just resistors. So in this case, any voltage is that you can equate to some current with some proportionality constant to it is going to apply to this super Ohm's law. And this applies to capacitors, inductors, and some other device, various other devices also that we can use. Okay. So this X here, we're going to call this the capacitance reactance. And I want you guys to start equating reactance with impedance, so that you can call it capacitance impedance, okay, because it acts as the same thing, okay. And we're going to define this XC to be I divided by omega t, okay. And then, so now we have Ohm's law, basically, for capacitor, where V equals I. Instead of R, you have this XC instead. Okay. Similarly, for inductor, I'm just going to do a quick review of inductors. So inductors are basically these devices where you curl a wire loop around, a, what's it called, solenoids, right? A lot of times you insert some material in here that has a high magnetic susceptibility, and therefore it actually increases the inductance. Okay, and I'm going to define inductance to be basically this letter L, and this inductance is going to be equal to the magnetic flux through this inductor divided by the current through this. Okay, and in SI units, it'll have units of this Henry, named after some other guy, right, with this H. In base units, actually Tesla, meter squared per amps. Okay, so, but just use Henry when you're using inductors. Okay, so the way this works is that you run a current through this little wire loops, a simple one. What happened is that using Faraday's law, right, you're going to produce a magnetic field that's going to run from right to left here. Okay, and this magnetic field that you're producing is going to be equal to the magnetic constant times the number of loops. So the more loops you have, right, the more magnetic flux it will get. Of course, the more current you do, the bigger the more current you run through this wire, the bigger the magnetic field you produce also. And it's inversely proportional to L, which is the length of this inductor. Okay, so if an inductor have N turns, what happens is that you actually pick up an extra factor of N, and then the flux is actually proportional to the area of each of these loops. Okay, so the magnetic flux through an inductor is going to be this mu naught. You pick up an extra factor of N from this N here, and then you pick up a factor of A, because now instead of dealing with magnetic field, you're dealing with the magnetic flux, because that's just P times A in the case of constant magnetic field. Okay, the I stays the same, and the L is just the length of the solenoid. Okay, so with that definition, we can plug that back into the original equation we have, and we just divide both sides by I, so the I's actually disappear. So the inductance of your device is actually mu naught N squared times A divided by L. We're gonna figure out, apply Faraday's law, where the voltage drop across this loop, the voltage drop from point A, right, which starts here, right, to point B, right. So in a device, you just have 2 points across this loop. It's going to be the time derivative of this changing magnetic flux over time. Okay, so what we can do, these equation numbers are not going to be relevant for your book. We'll cross that out. We're going to change this inductance to be basically this magnetic flux equation. We're just going to multiply both sides by I, right? So the magnetic flux is L times I. And if we take the time derivative of that, right, we get the delta V across the inductor. We're going to call that delta VL. Okay, right? So the only thing in this equation that depends on time is this current. Okay, so if we take the time derivative of both sides, right, the inductance stays the same because that's just the physical dimension and the number of loops and maybe the ferromagnet, the material that has a high magnetic susceptibility in it, right? So that's a constant. So this time derivative goes through, and then so the change in magnetic flux over time, and an inductor is actually just the inductance times how the current is changing. Okay, and that's going to give you a voltage drop across that inductor. Okay, all right. So that's sort of the backdrop of how in Steck he just props down this equation. So now we get to this equation where the inductance, in this case, I think in this textbook they use the negative, but we just care about the magnitude of the, so this is always going to be a voltage drop, right? So when you drop, the sign is actually negative, so that's why this negative sign is here. But in Steck he doesn't care about that, because now we're advanced enough so that, oh, we know that, oh, a high voltage to lower voltage means there's actually a negative change, right? So Steck actually start with this equation here to calculate the inductive reactance. Okay, in the complex notation we can replace the time derivative, remember, negative IW, I omega, right? In this case, if you do that replacement, oops, we end up with highlights. Okay, this negative I omega times L times the current itself, right? Because we just got rid of this. Okay, so now, right, if we want to find, this looks like something, right? Voltage equal to something times current, and that something is going to be our inductive reactance for the inductor. Okay, and therefore we have yet another super Ohm's law where V equals something times I. So for inductors, V equals to XL times I. For capacitor, right, I'll write this capacitor, right, it's going to be XC times I. For resistor, right, it's just going to be R. We don't use XR, but you can use XR if you want. It's the reactance or the impedance of a resistor. Okay, so these are the super Ohm's law where you can, these applies even to not just resistor but also capacitors and inductor. But be a little careful, it does have this imaginary number in it. It also has this frequency dependence, so these inductance actually depends on frequency, and it'll have this kind of phase shift because of the imaginary number.